the end of this unit. This unit consisted of 3 parts, and here we are going to go over those 3 parts just as a review, starting with graphing by hand. So graphing by hand is not that complex. We need to make a table, 1 column for t, 1 column for x, and 1 column for y. So let's do that. So t, x, and y. And we want to go from 0 to 10, so all right. Now, I'm not going to go through the whole entire table. I'm not going to talk about what I'm doing. I'm just going to go through a couple lines, speed up the video a little bit, and show you the finished product. So we substitute 0 in for t in both equations. So we get 5 minus 0 squared, which is 5. 3 times 0 is 0. So 5 minus 1 squared is 4. 3 times 1 is 3. Do the next set. 5 minus 2 squared, which is going to be 1. 3 times 2 is 6. So I'm going to go ahead and continue this here and see what we end up with. All right, so this is what we have. Now when we go to graph, we're not going to plot all these points just because of the scale of it. So let's say let's plot, from t0 to t5. So we have our coordinate plane. I pay attention to my x value and y values. If I'm going from 0 to 5, I just need to go to left to negative 20 and to positive 15. Okay. I think I'm going to count by 2s on my graph. So 2, 4, 2, 4, negative 2, negative 4, just to show the scaling. And then we have 5, 0, 4, 3, 1, 6, negative 4, 9, 2, 4, 6, 8, 9, negative 11, 12, so 4, 6, 8, 10, 11, 2, 4, 6, 8, 10, 12, and then 20, 15, 4, 6, 8, 10, 12, 14, 16, 18, 20. Let's count that again. 4, 6, 8, 10, 12, 14, 16, 18, 20, 2, 4, 6, 8, 10, 12, 14, 15. So when we plot these parametric equations, remember with each point we have to place the t value beside it. So we have t equals 0, t equals 1, t equals 2, t equals 3, t equals 4, t equals 5. All right, and we connect. Okay, and the last thing with our graph is we need to indicate the direction that it has gone. So we have, for this, we're going in this direction. There we go. There is our parametric equation in the graph of it. Look at the next one. Do the same kind of thing. We're going to create the table. I'm going to give you the first couple of values. I'm going to speed up so we can quickly get through this. So let's have our t column, our x, and our y. All right, so we're going from 0 to 2 pi. When dealing with radians, it's okay to go from 0 to pi over 2 to pi. It's not often that's a good increment. Okay, and obviously you could decrease this increment. You can do pi over 4 if you want to. It will give you a better visual. Okay, so I'm placing these values in, and let's see what we get. So 0, sine of 0 is 0, so 0 times 5 is 0. Cosine of 0 is 1, so 4 times 1 is 4. Okay, pi over 2, sine of pi over 2 is 1, so we get 5. And then cosine of pi over 2 is 0. All right, so I'm going to speed this up a little bit and see what we get as a finished product. Okay, there we go. So it's rather easy because of sine and cosine, there's a repeated pattern going on. Let's plot. my orange pen, is dying here. Not use it again. All right, so let's see what we have. So our first one, 0 to 4. Okay, 5, 0. 2, 3, 4, 5. 0, -4. -5, 0. And back up to 0, 4. So in this one, going and connecting what we have. Okay, now we have to label, so t of 0, pi over 2, t of pi, 3 pi over 2, and 2 pi. Now indicate direction. What's interesting about this graph, this parametric equation, is you might have thought initially that this was going to give us a circle. That would have been true if our coefficients were the same. But here, if we were to decrease our increment to get more points to plot, we would actually have an ellipse, or as common, many other people would say just an oval. Because notice what you could call radius, there's another word for it. It's 5 in the horizontal direction, but it's 4 in the vertical direction, so it's not the same. All right, but there's our plot. Moving on. What else do we have? Okay, so we have another one. So I'm gonna go through this. Again, this time I'm just going to go ahead and speed up the process a little bit by going ahead and going through the whole table, showing you what we get. Okay, let's do this. All right, so here's our table. Really, this equation might look rather challenging, but all you're doing is squaring your t-value, multiplying it by 4, and dividing by 5. And then you're subtracting 2. That's all you're doing. Squaring, multiply by 4, divide by 5, and subtract 2. Don't overthink it, guys. Please do not overthink it. All right, so we plot this. Okay, so I need to go -4 to 5, 2. That's the highest I need to go, and then I need to go 6 out this way. So let's do this. Okay, so we have 6. We have 6 and 1.2. 6, 1 and 0.2. 4 and -1.2. Okay. 2, -2. I believe a common mistake people are going to make here is accidentally looking at the t column and plotting, like I said, 0, I almost said 0, -2. Be careful with that. So once you've placed t in that column, we really need to not see it all. So if it's a matter of filling the table out, covering that up, let's do that. If we need to do that. If we're worried of making that mistake, cover that column up. So I'm going to do that here. So 0, -1.2. Okay, -2, 1.2, -4, 5.2. 1, 2, 3, 4, 5. Okay, and then we connect. We place our t's. We have t equals -2, t equals -1, t equals 0. Okay, now we indicate direction. And there we go. All right, so let's look at the last one. So once again, I'm going to create the table for you guys, and we'll talk about the graph. Okay, so we have our table. Again, for the square root function, don't overthink it. Simply placing 2 in, 6 times 2 minus 4. 3 times 2 minus 4 is is 2, so square root of 2. But the issue is we don't really know right from looking at this where the square root of 2 is. So we should find the approximations for each of these values. So I went ahead and did that for us. We get 1.4, 2.24, 2.83, 3.32, and 3.74. There we go. So there's going to be much easier to plot. Let's go ahead and make our grid. Noticing that we do not have a single negative value, we can just mainly draw our first quadrant. It's going to be good for us. Let's plot. So I'm going to cover up the T column. So we have 4 and 1.4. 1, 2, 3, 4. 1 and just below a half. 3 and 2.25. 2 and a quarter. 2 and 2.83. So it's past a half. 1 and 3.32. And 0, 3.74. All right, so there we go. Go ahead and mark T equals 2, T equals 3, T equals 4, T equals 5, T equals 6. Go ahead and connect our points. Draw our arrows. And there we go. It's important to recognize with this parametric equation that the t intervals, it's limited, okay? For example, I could not have a t value of 0. Well, you can look at this and think of why. So the t interval we have a function. Remember, if we have undefined within our table, that is represented by an asymptote of some sort. Most likely a vertical asymptote, actually. Now to say that out loud. So this is practicing graphing by hand. Moving on to eliminating the parameter. All right, so when we look at eliminating the parameter, our main goal here is to take a parametric equation where we have an x equals in terms of t, a y equals in terms of t, and rewrite it so it's y equals x, or even in the standard form. So let's look at number 5. So x equals 4 cosine t, y equals 4 sine of t. This one, I've shown you how you can walk through to get the end result here, but if we recognize that this is a circle, we can write it as a circle equation where we have x squared plus y squared equals 4 squared, which is essentially 16. You could write 16 instead, okay? So x squared plus y squared equals 16. So I'll take a link, put a link here on the screen so you can go back and check out the in-between stuff. But really, if you notice it's a circle, and we notice it's a circle first of all because the coefficients are the same and we have sine and cosine, that's a circle. So if you notice it's a circle, we can jump right to the end and write our equation. So looking at number 6. So number 6, when we actually have polynomials here, x equals and y equals and they're polynomials. The first step is to manipulate one of these so it's t equals. So I look at this and x looks to be much easier to manipulate. So I'm going to go ahead and work with that. So if we manipulate this equation, I can write this down again. I'm going to add 3 to both sides. Divide by -1. And we get negative x minus 3 equals t. All right. I am now going to substitute this into the other equation for t and simplify. So we have y equals 2, negative x minus 3 squared, plus 2 times negative x minus 3 minus 2.5. I went ahead and rewrote 5 halves as 2.5. And we simplify from this point forward. So we have, so you're just going through the solving process quickly. Okay. So we get positive x squared, we get positive 3x, and positive 6x, and positive 9. All right, and we get minus 2x because we're distributing, and then minus 6, minus 2.5. All right, we distribute the 2, giving us 2x squared plus 12x plus 18, minus minus 2x, minus 6, minus 2.5. All of this is on one side, so we combine like terms, which gives us an equation of 2x squared, let's see, plus 10x, and 18 minus 6 is 12, minus 2.5 is 9.5. And we identify, we have a quadratic function. So it's going to be good for us to know when we rewrite it, when we eliminate the parameter, what do we get? So if we were to plot, to sketch the graph for this parametric equation, we would get this graph, a quadratic. Let's look at the next. So x equals 1 over t minus 2, and y equals 4t plus 5. So you might think that working with y equals, that'd be easier to manipulate to get t equals. But then when I foresee us putting it into this equation, and we would have to solve for y, which would make it a little challenging then. We can actually solve this equation for t. Let me show you how. So I'm going to multiply both sides by t minus 2, okay? Which gives us t minus 2 times x equals just 1, because the purpose here was to cancel the 2. So we're left with 1. Now I'm trying to get t alone, so I'm not going to distribute the x. I'm going to divide by x, giving us 1 over x. Now I'm going to add 2, giving us 1 over x plus 2. All right? So then now we substitute this in for t, giving us y equals 4 times 1 over x plus 2 plus 5. So we solve for x by multiplying both sides by the denominator, manipulated it, got t equals, substituted it in, so now we distribute the 4, giving us 4 over x plus 8, and then plus 5. So we have an equation of y equals 4 over x plus 13. And this is a, I believe, if I remember correctly, it's the reciprocal equation, where we actually have an asymptote in this, but this is still a function. This is still a function. Okay, looking at number 8. So we have 2 of these. Thinking of which one would be easier to solve for t. Looking at the second one, I foresee us having to square root. Actually, you would have to square root to get t by itself. And the moment I square root, I'm going to have a positive and a negative, which I don't like the look of that. Just so you know, the only real time I'll look at manipulating y, the y function or equation, is if my x equation has a squared in it. So if my x equation has a squared component where I'll have to square root, I'll look at the other, okay? Often when that happens, that's also an indicator that my end result is not going to be a function when that occurs. But here, I'm going to tackle the x. So to get rid of the square root, we square both sides, okay? Then we add 7. That's t. Substituting this in for t, we get y equals x squared plus 7 squared plus 9. So I encourage you to write this out twice, x squared plus 7, and then multiply. So we get x to the power of 4, because x squared times x squared. We get 7x squared plus 7x squared, which is 14x squared. We get 7 times 7, which is 49. Then we add the 9, so it gives us an end result of x to the power of 4 plus 14x squared plus 58. This is a function, it's a polynomial of degree 4. Of degree 4, okay? So parametric equations, eliminating the parameter. There you go. Hope that helps. Moving on to projectile equations, or projectile motion. So we have our nice little formulas that we get to use for this. I say that we need to know them. Mainly, we need to know how to use them. The first equation, v of x equals v of x sub 0, that's saying that the horizontal velocity is constant. That's what that's saying. For the x equals, this will tell us the horizontal distance, how far away something lands. Make a note of that. So this x equation is how far away something lands. So horizontal distance, all right? So then the vertical motion, we have velocity equations and we have the displacement, the height equations. With the velocity equations, these are going to be the main tool to use when we want the time to maximum height. The time to maximum height, because at the maximum height, v sub y is 0. So we're able to set these equations equal to 0, and it's a two-step equation. So now with the last two, these are going to be perfect equations to use if we want to know when an object lands. When an object lands. Okay? So that's going to give you a time when an object lands, and if you desire to know how far away it lands, we take this time and place it back into over here. Okay? So let's check out some problems. So two golf balls are hit into the air at 6 feet per second, which is 45 miles per hour. Again, we're not going to really use that because 66 feet per second is good for us. And then at an angle of 31 degrees and then 49 degrees. If the ground is level, meaning y sub 0 is 0, that's saying y sub 0 is 0, estimate the horizontal distance traveled. So we desire the horizontal distance traveled, so we're going to be using this, but before we can use this, we have to find the time it lands. Okay? We have to find the time it takes to land. So let's go through this. So we're going to use our displacement equations. Now, since we're dealing with feet per second, remember that means we're using the minus 16 equation. So we want, write this down, y equals y sub 0 plus v sub y sub 0 t minus 16t squared. Now we're going to plug everything in. We're looking to see where it lands. So our desired height's 0. Our initial height's 0. Okay, so that's I'm not going to write anything there. V sub y sub 0, this is the y component of velocity, which is velocity multiplied by the sine of our angle measures. Let's do 31 degrees first. So we have that, and we multiply that by t, and then minus 16t squared. All right, so we solve this. I'm actually going to go ahead and write the other one too. So we have same equation, so we have 0 equals 66 sine of 49t minus 16t squared. Again, we're using the minus 16t squared because we're measuring in feet. So looking at the first equation, when we solve this, both terms have a t, so we can factor the t out. So 66 sine of 31 minus 16t, okay, which says the height's 0 at 0. Well, sure, that's at the beginning, but the height's also going to be 0 when our other factor is equal to 0. So we have our other factor, 66 sine 31 minus 16. That is a two-step equation. When we solve it, we'll get t equals 2.1245 seconds. That's the time it takes to land. All right. And then we desire the horizontal distance. Let's go ahead and solve the other one with it. Same idea. Factor t out. We get z equals t 66 sine 49 minus 16t. Okay, so we're going to set 0 equal to 66 sine 49 minus 16t. When we solve that, we get a t value of approximately 3.1132 seconds, and that's to land. Adding that little bit on the end will help us remember what these numbers are for. So now to find the horizontal distance, that looks like using our x equals equation. So x equals our initial x, we always typically assume that that's 0. So horizontal velocity, that's going to be 66 cosine of 31. and we multiply by the time, 3.1245. Over here we would have x equals 66 cosine of 49 times 3.1132. And we get distances of, first one, approximately 120.1894 feet. And then for the other, we get approximately 134.8012 feet. All right. So I just saved time by going and computing it for you, but you can place these in real easily, making sure you're in degree when you go to solve it. Let's go and highlight, box this in so you can see the results. All right, so let's look at the last problem. So a football is kicked at an angle of 32 degrees with a velocity of 20 meters per second. Assuming the ball leaves the foot at ground level, so y sub 0 is 0. So what is the maximum height? Okay, so we can at least find the time to the maximum height. Remembering here that the time to the maximum height we can find by setting our velocity equation. So we're measuring in meters, so we're using the 9.8. So we can set this equation equal to 0 because that's going to give us the time to the maximum height. So that's 0 equals, our vertical velocity is going to be 20 sine of 37. Almost made a mistake there. Minus 9.8 t. So when we solve that, we get a time to the maximum height, 1.2282, and this is seconds to max height. Now this isn't the maximum height, this is the time it takes to get there. So we have to get a height equation to plug this into. So our height equation is going to be y equals y sub 0 plus v sub 0 y t. We're using meters, so it's going to be minus 4.9 t squared. Okay, let's plug numbers in. We want to know what y is, so in our initial y is 0. There we go. So we have v sub 0y, which is 20 sine 37. Our time is 1.2282. Okay, minus 4.9, 1.2282. We square that, and you get approximately a height at the max of 7.3915 meters for the max height. Okay, so box that in, box this in over here too. Okay, so moving on. That's all for part A. For part B, the time traveled before the football hits the ground. So we have a height equation again, and we're setting the height equal to 0. All right, we're setting the height equal to 0. So we already have our equation. It's going to be 0 equals, so this is part B now. 0 equals our initial height of 0. All right, 20 sine 37 t minus 4.9 t squared. Yes, we factor out a t, and eventually put little dots here, dot, 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 dot. You have 0 equals 20 sine of 37 minus 4.9 t. Just skipped a couple steps. When we solve that, we get a time of approximately 2.4564 seconds. This is to land. All right, good. Part B's done. And how far away does it hit the ground? So in part C, we now use a horizontal equation. We use a horizontal equation with the time that we got to do this. So x equals, we need the horizontal component, which is 20 cosine of our angle multiplied by the time to land. And when we evaluate that, we get approximately 39.2354, and we say meters away. It lands roughly 40 meters away from where it is kicked. All right, so projectile motion problems, really knowing when to use each equation. Again, once you know how to use each equation, it's a matter of a lot of computation. Okay, so you really need to persevere through these problems, guys, and just not give up. We're at the end. So I wish you the best of luck as you continue reviewing for this unit, preparing for the end of the unit assessment. I look forward to talking to you guys more in the next unit, and until then, good luck.